Hello everyone, happy Tuesday. Hope that you're having a good one. Going to talk today about some higher order polynomials, but first let's do some bell work using quadratic forms. So here we're just going to talk about what we can do with each quadratic function that we have here. So these are written in three different forms that we talked about yesterday. This first one is written in vertex form. It's vertex form because it's written like it was translated, right? This plus 4 in here does something to the x's, this plus 2 out here does something to the y's. This second one here is written in factored form because we have it written in its two factors, factored form. And then this last one is written in standard form, standard, because we have that ax squared plus bx plus c. And so each of these tells us something about the polynomial, about the quadratic. Let's see what we can say. So right here we know that the x does the opposite of what you want it to. So our vertex here, our vertex is -4, 2. And we can't really say a whole lot else about this. This 1/2 tells us that it's undergone a scale change, a vertical change, a vertical shrink down to 1/2 its size. So we can maybe graph a sketch here. -1, 2, 3, 4, and then up 1, 2. So that's where our vertex is. It's not reflected at all because we don't have a negative anywhere. And then we have that that shrink of 1/2, so it's going to be look a little bit wider. So it might look something like that. But we can't really say exactly where it crosses the y-axis. Some of our other forms are better for that. So let's look at this next one that's a factored form. So the things that gives us right away are the x-intercepts. So our x-intercepts on this guy, our x-intercepts are going to be x equals 6, because if x is 6, this is going to cancel out to 0, because the x-intercepts happen on the x-axis along here, and so that's going to be when the y-coordinate is 0. So we set it equal to 0. 6 is going to cancel that guy out. Also, x equals -1 is going to be our other one. So there's our -1. Here's our 1, 2, 3, 4, 5, 6. So we have our two roots right there. And if you remember from yesterday, we also could get the y-intercept pretty easily from this one. We just have to multiply those two constant terms together. They're both positive this time. It looks like that value is going to be +6. So our y-intercept there is +6. We go up to 1, 2, 3, 4, 5, 6 right there. So we know where our y-intercept is. We have our two x-intercepts. We kind of get a picture of what that parabola is going to look like. We can draw it in. Something like that. Okay. So we get a good picture of what's going on just by getting those intercepts right there. This last one's written in standard form. So standard form is the one that we kind of have to do a little bit more math with. The y-intercept's really easy to get. The y-intercept right here is just 6. It's our c value. All you have to do is just get it right there. So we know we have a y-intercept of 6, just like we did on the last one. 4, 5, 6 right there. And then what else can we say about it? Well, we can find the vertex by doing -b over 2a. So that's -4 over 2a. Well, a is just 1 out there. So 4 over 2, which is a 2. That gives us the x-coordinate of the vertex. Then to get the y, we have to do f of 2, which is going to be 2 squared is 4, minus 8 plus 6. Looks like what is that? -4 plus 6 is 2. So 2, 2 is where our vertex is. Right there. That's our vertex, that's our y-intercept. It looks like we don't go through the x-axis at all. So it looks like it comes down and hops back up like that. So we could use quadratic formula to try to find the x-intercepts, but if you look over here, well, there are no x-intercepts, so we'd probably have some i's involved or something there. But we see that we can figure out what this parabola looks like without even finding the x-intercepts, because we have the vertex and the y-intercept. We're going to do a little bit more with that one because I know that you guys get nervous whenever we complete the square. So we're going to do one completing the square problem here, and hopefully it's going to make a little bit more sense to you. Our goal here is to get vertex form, a times x minus h squared plus k. And to do that, I mean, this guy right here, that is a factored perfect square. And when we were doing transformations, we didn't really see that because we were like, well, it just looks like it's been moved. We replaced x with an x minus h. That moves it h units in the left or the right direction, depending on if h is positive or negative. And we didn't really think much more about it. But if you were to expand that out, it would be x squared minus 2xh plus h squared. So if we can somehow get our equation to look like that, then we could factor it here and we would have it in vertex form. That's the whole point of doing this completing the square. And it works similar to how we did it before, but it's a little bit harder. So what we're going to do is we're going to just forget about that 6 for a second. So we have x squared minus 4x here. And what we're going to have to do is we're going to have to add something and subtract it in here. Because if we add something, we can't just add something on the right side. We'd have to add it on the left, but that would be weird. We'd have to move it back to the other side. So we're going to add and subtract something in there, and then that plus 6 is just hanging out at the end. What we always add is that b term divided by 2 squared. Because if you take this, divide it by 2, that would be negative 2h divided by 2, and square it, it's the h squared. So that negative 4, we take it, divide it by 2 every time, and then square it. Negative 4 over 2 is negative 2 squared is a positive 4. We add 4, we better subtract 4 as well. But then we have no coefficient this time, so we don't have to worry about that distribution mess we had to do last time. This time we just take this part right here. We're going to cut off our parentheses. So I just made this parenthesis a little bit smaller in here, but we still have a 0 here. We didn't add anything or subtract anything. We just added a 0. So this part here we can factor. That's a perfect square. So that is x minus 2 quantities squared. Then we have a negative 4 and a plus 6. That makes a plus 2. So that tells us our vertex should be at 2, 2. And let's go back a slide and see if that's what it was. Hey, thank goodness. Our vertex was 2, 2. That's good. Right? It's right over there. So we have our vertex form. So we know it has a vertex at 2, 2. And it hasn't been done any scale change or anything, so it's just going to look like a parabola sitting right there at 2, 2. Can't find our y-intercept, but we see up here that it's at 6. So 3, 4, 5, 6 probably goes through right about there. And there's our parabola. So the completing the square, it's one of those things where it's nice when you're converting between forms, and it's just something that's going to pop up a few times this year. And if you need more help with completing the square, please come and see me. It's something that after you do a few times, it's not so bad anymore. So it's worth looking at. All right. So 2.3 is higher order polynomials. So yesterday we talked about quadratics. Quadratics are only the second degree polynomials, like ax squared plus bx plus c, and then the other forms that we saw of that. Today we're going to go a little higher, like a cubic maybe, or a quartic. All right, so these are going higher in order. So cubic would be like x cubed plus 3x squared minus 2x plus 1, something like that. The quartic is the fourth degree, so maybe just like 3x to the fourth. That's a quartic. Doesn't have any more to it, but it's a quartic. So we're going to see some stuff we've seen before, and we're going to see quite a bit of stuff that might be new to you as far as polynomials go, because there's all kinds of stuff that you can study with polynomials. So we're going to start by thinking about something graphically here. If I was told you to graph this by hand, you would probably have no idea what to do, because you maybe would make a table and try some values and start plugging things in, but the idea of what this thing looks like is pretty challenging. But by the end of today, we might have some more tools as far as how to graph something like this. And where we're going to start with this is I'm going to tell you actually how this ends up factoring. So this guy right here is going to factor into x minus 1 times x plus 2 times x minus 3 times x plus 1 times x minus 2. Now this didn't come from anything. I mean, I didn't just know this by looking at that equation up there. That'd be pretty crazy. This is just, I'm giving it to you. I'm telling you that this is what it looks like factored. And I want you to think about how many factors there are and why that makes sense. Here I count 1, 2, 3, 4, 5 factors. Because if you multiply all these factors together, you're going to have 1, 2, 3, 4, 5 x's. When you multiply x by itself 5 times, that's x to the 5th. There could not be a 6th factor here. Because if there was a 6th factor, we would have x to the 6th. Our degree would be too high. So we don't have that there. The most factors we can have here are 5. So what does that mean? Well, that means we can only have 5 roots. So if you ever graph something that's a 5th degree, it could look like this. Cross once, twice, 3, 4, 5. But it couldn't cross any more times than 1, 2, 3, 4, 5. It could cross fewer, like maybe you'd have something like this. It could just go 1, and then maybe it goes through 1 more time or 2 more times. But it's possible that like it misses some of those turns. So it could have fewer, but it couldn't have more than 5. If there were more than 5, then we would have a 6th or a 7th or an 8th degree polynomial. We wouldn't have a 5th degree. So this brings up something important about the number of zeros and also the number of times a graph can turn. Because if a graph turns too many times, it could go through the axis an extra time. And that's not okay because these are the only zeros we can have here, right? These zeros are going to be x equals 1, x equals -2, x equals 3, x equals -1, and x equals 2. Right? Those are our 5 zeros that we have here. And I actually have this set up on Desmos, so I can actually show you exactly what this looks like. Keep those. So let's go over to Desmos, and here's that graph. So I've got it in factored form right here, and we see it goes through at -2. Let's see what we had there, but I think it was -2, -1, 1, 2, and 3, and those are our zeros right there. And we notice it turns then once, twice, 3, only 4 times. If it turned a 5th time, it would go through the axis again, and that would be too many roots. So this is what leads us into this whole idea of what's happening with these turning points and the zeros of the polynomial. So if you have a function, f of x, oh, we changed colors. That always happens when I switch. Oh, I'll go with red for a little bit. Why not? So if we have f of x equals a n x to the n plus a n minus 1 x to the n minus 1, etc., that long polynomial definition. And then last we finish with a1x plus a sub 0. That's our constant term. Whatever this n is going to dictate it. So if our degree is n, then we can have at most, if I could write, we have at most n zeros, and at most n minus 1, I'm going to call them turning points. Okay, and those turning points, what those really are, those are local extrema. They're local extrema. And we can see that from the graph we were looking at. Because in that graph, let's see if I can get it back here. So in the graph that we had, it's so slow. Oh, come on. There we go. So in the graph, we see that we had 1, 2, 3, 4 turning points, which is one less than the degree we have here. Now we don't have to have that many. That's why it says at most, because if you think about it, excuse me, if you think about it like y equals x to the 4th, y equals x to the 4th looks like this. It gets pretty flat down. Whoop, if I could draw. It gets pretty flat down by the axis, and then it just pops right back up. It looks a lot like a parabola. It only has 1 0, and it only has 1 turning point. So that's why it's this at most idea. It has at most n zeros and at most n turning points. So what this is getting at is if you have a graph that looks like this, we see we have how many turning points? We have 1, 2, 3. And if you drew an axis in here, maybe something like this, it could possibly have 1, 2, 3, 4 zeros. So what does the degree of this polynomial have to be at least? Well, it's got to be at least 4. N is going to have to be greater than or equal to 4. It could be bigger, right? Because we just saw here, if we have 1 turning point, well, we have at least a degree of 2. But over here, if we have 3 turning points and 4 zeros, we got to have at least a degree of 4. So that's kind of what's helpful for this. You're going to see some matching problems in your homework tonight. It's going to deal with stuff like that. So after we talk about turning points and zeros, we want to talk about end behavior. So looking at these two functions, f of x and g of x, we're going to talk about how they're different and how they're the same. So these two functions, they have the same leading term we call here, right? Each one of these is called a term. But this guy right here, this x cubed, is going to determine the end behavior. So we're going to look at these two graphs again on Desmos, and let's see how they look the same or different. So here we are. Let me turn off our first function. So here is the function f. So this is f of x. I'm going to zoom out just a little bit. And we see we kind of have some curvy, swervy stuff going on here. One of the things that they talk about in this section that we're not going to hit on real hard, but what's happening is if you zoom out a lot, it kind of looks like x cubed. It kind of looks like it comes up and through the axis and then keeps going. In the middle, though, this 4x squared, negative 4x squared, negative 5x, and negative 3, they have some kind of an influence on the function. Let me show you what it is. So negative 4x squared, that would be a downward-facing parabola right crossing the 0 right here. So if it's going to be a downward facing parabola, it's influencing this part of the graph. It almost looks like a downward facing parabola close to the center there. That negative 5x, that would be a line with a slope of negative 5 coming right through here. This section of the graph right here looks a lot like a line with a slope of negative 5. Then the negative 3, that just moves it down 3. So that's just going to move it down to that point right there. And so that's really what's happening in this graph, and that's where those points are coming into play. The reason that's important is because those three terms have a lot of influence on what happens at the graph at what I call its center. So the center of the graph here, it's influencing a lot, but that x cubed out front is the only thing that really matters for what's happening when x is really negative or really positive. And let me show you what I mean. If we turn this guy on, and now in the middle, we see these look very different, but let's start zooming out. If you zoom out, you start to see that, man, they're almost identical on the left side there. I mean, our x is not very small yet. The y's are pretty small, but we're not even very far to the left. And on the positive end, they're also looking very, very similar. So a little bit different in the middle, but all that matters, we call it the dominant term, is that one with the highest degree. So that term with the highest degree there is one that's going to matter the most. I'm going to change these settings just a little bit so we can even see it better. I'm just going to change my x coordinates to go from negative 50 to positive 50. So we're just going to get a better view of what's going on here. And I'm going to change my y-axis. I'm going to go from like negative, I don't know, I might have to go to like 4,000. Oh, even worse. We'll probably go like to negative, I don't know, 100,000. Look at that. And then our y max I'll change to 100,000. All right. So we see in the middle, now we can hardly even tell the difference. I mean, at the ends, it's really looking like those functions are getting close to be the same thing. So that x cubed out there is really what's going to change the end behavior of our function, just that leading term. So let's talk about end behavior. So in general, all that really matters is the leading term. So if we have something, back to red, back to purple maybe. So if we have a function, f of x, if it's a polynomial, we have a n x to the n, and I'm just going to write plus blah, 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 because all the rest of it doesn't even matter to the end behavior of the function. So we have a n x to the n plus some other stuff. The leading coefficient, and that degree are the only things that matter to the end behavior. So our leading coefficient, and we have our degree. Those are the only two things that are going to have any kind of bearing on our functions. So there are four possible cases here, right? We have two things, and they could be positive or negative and even or odd, and that's all that matters. So the first one I'm going to consider is if we have a positive leading coefficient, so an is greater than 0, and then we have a degree, let's say that is even. So an example of this could just be y equals x squared. Right? We have a positive leading coefficient, and we have an even degree. Well, our end behavior there, we know what that looks like. It goes up to the left, it goes up to the right. And then what happens in the middle here, if it was x squared, it would just come up like a parabola. But anything could happen in here. As long as it's an even one, it just has to somehow end going up on the left and up on the right. Now this is where that limit notation is really going to come into play, and we're going to be using this for the rest of the year. So over here, what this is telling us is the limit. So this is how you say it. You say the limit as x approaches infinity. That means as x is getting really, really big. Okay, so as x goes to the right, limit as x approaches infinity of the function, or of f of x. Well, as x goes to infinity, where's the function going? It's going to positive infinity. And as x goes to negative infinity, what's happening to the function? Well, it's going off to positive infinity as well. Okay, so limit as x approaches negative infinity is also positive infinity. So it's going positive on the left and positive on the right. Let's see what's happening if we have a positive leading coefficient and our n is odd. So for example, we could have like, I don't know, f of x equals x to the fifth, let's do like 3x to the fifth, minus 2x squared plus 1, something like that. So this is the blah, blah, blah. No one cares what's happening over there. All that matters is our leading coefficient. We see it's positive. We have a 3 there. Move that equal sign maybe so we can see a little better. There we go. So we have 3x to the fifth minus 2x squared plus 1. So this time, this is going to be like x cubed, right? X cubed is that lane change, like that. As we go to negative infinity, if you put a negative number into something to an odd power, it's going to go down, 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 down. Because a negative number to an odd power is going to be very negative. So we're going to have something down on the left. But if you put in a very big positive number, like 1,000 or 1,000,000, and you take it to fifth power, it's going to stay very positive. So it's going to go up as we go to the right. Now what happens in the middle here again, I don't really care about. We're just talking about the end behavior. It might be like that. It might go 100 times back and forth, doesn't matter. But for sure, it's going to be down to the left and up to the right. So again, we write that limit as x approaches positive infinity of f of x. Well, as x goes to positive infinity here, f of x, the function, is going to positive infinity. What about as x goes to negative infinity, though? As x goes to negative infinity to the left side here, our function is going down. So this time, it's negative infinity. So as x goes to positive infinity, we're going up. Negative infinity, the function is going down. So now let's see what happens if we have a negative leading coefficient. So if an is less than 0 and n is even, in this case, let's say that we have, well, we have to have a negative leading coefficient. So let's look at negative, I don't know, negative 4x to the fourth plus x cubed, just something like that. This is the blah, blah, blah. It doesn't matter. So that negative, we learned this back in 1.6. That's transforming the function. It's reflecting it over the x-axis. So it's going to take this and it's going to flip it all down. So we have the same kind of shape, but it's now reflected over the axis. So it's going to be down on the left and down on the right. You notice when it's even, when we have an even degree, they go the same way. So I don't know what happens in the middle. Doesn't matter. But we know that it goes down on the left and down on the right. So the limit as x approaches negative infinity of f of x here is negative infinity because it's going down. And the limit as x approaches positive infinity, so as x is getting bigger and bigger and bigger, the function is getting smaller and smaller and smaller. So we've only got one option left here. If you want to pause the video and think about what this is, and think about what this is actually going to look like, might not be a bad idea. So if you want to do that and try it now, you could do that. All right, I hope you're back with me now, and let's see if we end up sketching the same thing. So in this case, we have our leading coefficient is less than 0, and we have our degree that is odd. So that negative again, so for example, we might have f of x equals, I don't know, negative x cubed. Doesn't matter. Negative x cubed. Okay, so that's going to flip it over the x-axis again. So instead of going down here, it's going to actually go up. Then something weird's going to happen in here. I don't know. And then it's going to end up going down. So the limit as x approaches positive infinity of f of x is going to be equal to negative infinity. So here we're going down. As x gets bigger and bigger, the function is going down. As x gets smaller and smaller, though, the limit as x approaches negative infinity of f of x. Here we see that the function values are actually going up. So this is equal to positive infinity because it's going upwards. So this takes some practice as well, but after a while you see, okay, leading coefficient's negative, coefficient is, or the degree is odd, so that means that I must have some kind of a shape like this. We're going to get some more practice with that today. So let's talk more a little bit about factored form. So the first thing that comes with factored form is actually factoring. Now we haven't done a lot of factoring since we did the chapter P stuff. We are going to see a whole lot of factoring in this chapter, so you're going to get good at it if you're not good at it yet. So let's take a look at this. The first thing we notice here is everybody brought an x to the party. So let's factor that x out. So we got an x times x squared minus x minus 6. So I just pulled out the GCF, the greatest common factor there. Now this guy we can factor. We could factor with trial and error and x box. Yesterday I factored with trial and error, so let's make an x this time. 1 times negative 6 is negative 6 That middle term is -1. We need two things that multiply to -6 and add to -1. I think -3 and 2 will fit that bill. So it looks like this is going to be x, times x minus 3 times x plus 2. Let's double check. X squared plus 2x minus 3x gives us a -x minus 6. Perfect. So we have our factored form here, and we talked about yesterday was it's real easy to get those x-intercepts. So the x-intercepts here, it looks like are going to be 0. Okay, that's new, okay, because over here, if x is 0, we for sure have it. You could write this as x minus 0 if you wanted to, but we don't usually do that because subtracting 0 does nothing, right? But so our x-intercepts are 0, and then this to cancel out, I would need a 3, and here I would need a -2. So we have our x-intercepts, 0, 3, and -2. So if we wanted to sketch a graph of this, let's see, 0 is right here, 3 is at 1, 2, 3, and then a -2 right there. Now we can almost sketch a graph of this. Those are the only places it crosses the x-axis, but what we don't know is the end behavior. Well, we can figure that out. We got an x cubed here, right? So our degree is odd, and our leading coefficient is positive. So we can go back and look at our chart. We have a positive leading coefficient. We have an odd degree, so it's going to look something like this. In fact, this probably looks a lot like what our polynomial is going to look like. So we know it's got to start down there somewhere, and it's got to end up here somewhere. So we can kind of just draw it through and see what it's going to look like. So if I had drawn it correctly, it would go through at those 3 spots we talked about, and we have a pretty good sketch of our function. That's pretty cool. And that's all you have to be able to do with the factoring and graphing. Now, sometimes it's a little bit more complex. So what are the roots of this guy? If we set this equal to 0, what are the zeros going to be? Well, looks like it's 2, 2, and 2, and -1, and -1. So we have these roots coming multiple times. That's why they're called multiplicities. It's like we have 2 is a root 3 times, and -1 is a root twice. But you can only go through the graph at 2 once. And you can only go through the graph of -1 once, because if you went through twice, like it would have to come around, it wouldn't pass the vertical line test. That'd be weird. So these multiplicities, what's going on is something special happens at those spots. So it can't just go through like a normal route. It has to do something kind of special there, which is what brings up this whole idea of multiplicities. So let's talk about what happens there, and then we'll come back to what this graph is going to look like. So multiplicities, you either have even multiplicities or you have odd multiplicities. So even means like if you have f of x, the function we were just looking at, we could write that x minus 2, x minus 2, x minus 2. So we could write that as x minus 2 cubed times x plus 1. I think it was squared, right? Yeah, we got 2 of them, so it's going to be squared. So this is our function, right? And it's written now in factored form, and it has these powers up there. So this we call multiplicity 3. And this we call multiplicity 2. So we have a multiplicity of 3 here, and we have a multiplicity of 2 over here. And what happens if you have an even multiplicity, what happens is we say it bounces on the axis. So if we had an even multiplicity right there, it would bounce. Instead of going through like a normal root like we had in our last equation, right? It went through because we had all single roots here. There were no powers, just went straight through. So what happens now is it's going to bounce on the axis. Some people say it kisses the axis, but I think it's kind of nerdy to say that, you know, kiss my axis, right? So right through there. So an even multiplicity, it's going to bounce on the axis. And the odd multiplicity, what happens here, some people say, so this is a bounce, or a kiss, if you want to say. The odd multiplicities, they go through, but they go through kind of in a flat way. So they go through, but they go through kind of flat. So what that means is, let's say that at that same point we had an odd multiplicity. It could come through like this. So it's going to like flatten out, like it's going to bounce back up, but then it's going to go through and kind of come down like that. So it doesn't just go straight through like we would with a normal single multiplicity. It kind of flattens out and goes through. So you could have it coming down from the bottom or up from the bottom, and it could go through like that, just like we could bounce from the bottom as well. It could come up and bounce like that. Yeah. So that's what's going on when we have these multiplicities. And you only really see that if it's in factored form like this. So let's try an example. So we're going to sketch the graph that we were talking about before. So we have our zeros, our x equals 2 and x equals -1. Usually what you do now is you write out the multiplicities. So multiplicity of 2 is a 3, so that's an odd multiplicity. And the multiplicity of, that's -1, sorry about that. -1 is 2, which is even. Now the last thing we have to think about is what the heck is our end behavior? Well, the end behavior, let's see here. If we wrote this out like we saw it originally, we would have 3 x's. So we'd have x cubed, and we would have an x squared. Multiply those together, you have an x to the 5th. So we have a degree that is odd. Right? We have a degree that is odd. And we also have a leading coefficient. There's nothing in front of here. So our an is greater than 0. So our end behavior looks like we're going to start from the bottom, and we're going to end at the top. And then our roots are right here at -1 and at +2. So it's got to go through at those two spots. -1 has an even multiplicity, so it's going to come up, it's going to bounce, just like that. And then we're going to come back up through here. It's going to be flat for a second because we have an odd multiplicity there. And then it's going to come up and it's going to join that guy and it's going to go off to infinity. So you notice these graphs aren't always the prettiest things, but as long as you're getting the right idea as far as the sketch, that's what I'm looking for. You know, did you flatten out for the root? Did you bounce for this root because it was an even multiplicity? Those are the kinds of things that I'm looking for. Nothing else. Let's do one more example. So this one's got all kinds of roots. Now, why don't you pause the video and give this a shot yourself? Remember, we're thinking about end behavior, so how many x's do you have? And then what's happening at those roots? So take a second and try that on your own. All right, welcome back. Let's try this together. So it looks like our roots here, I'll write out my roots, -3, 2, -1, and 6, and that's also our multiplicities. So the multiplicity here, this is a multiplicity of 1, this is a multiplicity of 2, this is a multiplicity of 3, and a multiplicity of 1. So those 1's just go right through. This one's an even multiplicity, it's going to bounce there. And this one's an odd multiplicity, so it'll go through, but it'll be flat when it does that. So altogether, what's our degree? 1, 2, 3, 4, 5, 6, 7. So our degree is 7. If you multiplied all the x's together, you would have an x to the 7th power plus a whole lot of blah, blah, blah. Because that x to the 7th is the only thing that matters for our end behavior. Positive leading coefficient and an odd degree. So it's going to have end behavior that looks like that. So let's see what's going on. Looks like we have to do our roots up to 6 from -3 to 6. Let's go to -1, 2, 3, +1, 2, 3, 4, 5, 6. Okay, so we have root 6, root -3, -1, and at 2. So let's check our multiplicities. -3 is just a single multiplicity, so it's just going to come through there. End behavior means we're going to start down. And then at -1, we have an odd multiplicity. This is going to come through, but it's going to be flat. So we have a flat one there. And then at 2, we have an even multiplicity, so it's going to bounce. And then at 6, we have a single multiplicity, so it just goes right through like that. Matches our end behavior, and we were able to satisfy all of our roots. Tomorrow, we're going to do a little bit more with factored form. You're going to have a worksheet to fill out. And you're going to do a lot, and the last thing we're going to add there is y-intercepts. So how do we find that y-intercept? We talked about it a little bit. It's a little harder with these multiplicities, but it's really not much different. That's all I've got for you. Give this homework a shot. A lot of stuff like what we were doing in the examples today. If you have questions, please email me. I got only one email yesterday about a video not working. If that does happen, please do email me in class if that's the case. And I will try to check my email periodically and get back to you. Also, we brought up the whole idea of the pirates yesterday, and I wanted to talk through the solution to this. So remember what happened. We had pirates numbered 1 through 1,000, and each pirate knows what their number is. So pirate number 1 knows that he's pretty safe, because even if everyone else gets killed, he'll still get all the gold. Pirate number 1,000 is pretty nervous because he might get killed. So the strategy here is, well, if there's one pirate left, he gets it all. So he gets gold. If there are 2 pirates left, a lot of people answer that there are 2 at the end. Well, let's see if that makes any sense. If there are 2, yeah, it'll stop because pirate number 1 will say, let's kill him. Pirate number 2 will say, please save me. And so the 2 of them will be at a deadlock. So they would also split the gold. So it would end there. These are places where it would end. they would split the gold. But the question is, how the heck did they get down to 2? Because 2 pirates can only kill 1 person, right? Because they could only have a majority when there's 3. If there are 4, they don't have a majority anymore. So everyone always like, oh, it must be 2 pirates because that's where it would stop. But there were 1,000 to begin with, and you would think maybe pirate number 3 at some point would stop voting to kill people if he knew it was going to get down to him. So at 3, yeah, 3 would be done because 1 and 2 would vote to kill him. But what about at 4? At 4, let's think about what 1, 2, 3, and 4 each would have to say. 1 and 2, they know, hey, if we kill 4, we can kill 3, and it'll be down to us. 3, though, is thinking, if 4 dies, 1 and 2 are going to kill me for sure. And 4 wants to save himself, so 3 and 4 are going to vote to save. So at 4, they actually end up splitting the gold. So it's a split. Now, right about here, everyone's like, oh, so it's even numbers, so it must stay at 1,000. Well, let's keep going. Those 4 know that they're safe. How many can they kill? Well, at 5, they could for sure kill 5. At 6, the 4 of them could kill number 6 and number 5. At 7, it would be 4 to 3. 7, 6, and 5 will get killed because 4 knows, hey, we can just keep killing people until it gets down to me because 3 is going to have my back at that point. But what about at 8? At 8, these 4 are like, hey, we want to kill because it'll get down to us. We'll have more gold. But 5, 6, 7, and 8, they all know that, hey, if 8 dies, I'm toast, I'm toast, I'm toast. So they're all going to vote to save number 8. So at 8, they also split. Do you see the pattern? 8 can kill all the way up to number 15, 14, 13, 12, 11, 10, 9, but they can't kill number 16, which can't kill number 32, 64, 128, 256, and pirate 512. 512 pirates will split the gold because that's the highest power of 2, less than 1,000. Pirate 512 knows he should kill all the way until it gets down to him. And then once 512 dies, these 256 pirates are going to kill all of them down to 257. So 512 is where the voting will stop, and that's the number of pirates that will split the gold. Kind of cool. I love you guys. That's why I'm here. Have a great day. And tomorrow you'll have a short video, and then you'll be doing a worksheet for most of the time. Have a good one.